Okay, so we have a conical tank, 10 feet across the top, 12 feet deep. When you're drawing these pictures, you don't have to draw a three-dimensional picture. It's actually easier if you just draw the cross-section of the shape. If we were to slice, not cross-section I guess, but a vertical slice through the center of a cone, what shape would we see?
A triangle.
See a triangle, right? So it's easier if you just draw a triangle to do the problem than it is if you try to sit there and deal with having a cone. So the tank is 10 feet across the top and it's 12 feet deep. Water is pouring into the tank at a rate of 10 cubic feet per minute. What does that 10 cubic feet per minute represent?
Derivative of the volume.
So how would we write that?
dV
dt. So we know dV dt equals, is it positive 10 or negative 10?
Positive.
It's positive. The amount of water is getting bigger, not smaller, right? It's going into the tank, not coming out.
Unless they forgot to plug the tray.
Okay. All right. You know what was really fun on one AP exam? They had a tank, a cone here and a cylinder below, and they had the water coming out of the cone and pouring into the cylinder below, and they did like a double related rates kind of a thing. It was fun. That was an interesting problem. So anyway, so dV dt is 10. Find the rate of change of the depth of the water when the water is 8 feet deep. So we need to draw the water. So I'm going to put that the water is like here, because it's about 8 feet deep. And I'm going to let H represent the depth of the water in the tank. So what are we trying to find?
The rate of change.
The rate of change of the depth of water. So how would I write that?
dHdt.
dHdt is what we're trying to find. I don't use D for depth. I use H for height for a couple reasons. So otherwise you'd have d dt, which is confusing. Plus, in your volume formula, it's H, not D, so I use H. All right, when the water is 8 feet deep, so when H equals 8. Okay, so we've written what we're given. We've written what we're trying to find. We need an equation that relates the variables. What would be a good one to use?
No idea.
Volume of a cone, right?
Which
Might be a good one to use. Now, if this was a quiz or a test or the AP exam, they will give you volume of a cone, right? So, volume of a cone is 1/3 pi r squared h. If you want the volume of an object that has a uniform cross-section all the way through, the same size and shape cross-section top to bottom, it's just area of the base times the height for whatever the shape is. If the shape goes to a point, so it's a cone or a pyramid or anything like that, then the volume is 1/3 area of the base times the height. Right? So for a cone, it's 1/3. What shape is the base of a cone?
circle.
It's a circle, pi r squared, times the height. Right? So that's how you get your volume formula. 1/3 pi r squared h. We know dV dt. We want dH dt. Do we know or want dr dt?
We do. 10.
Is it listed over here?
No.
No. If it's not listed, we need to get rid of that variable.
Okay.
Now, how do we get rid of a variable? Sometimes in the problem, they'll give you the information straight up to get rid of it. There's one problem in your homework tonight where they specifically say something like the height is 3 times the radius. In which case then, you can just, like if they tell you, don't write this down, but if they say, hey, the height is 3 times the radius, so then you could just say, oh, the radius is 1/3 h, and just plug that in for your r. Okay? So if they give you the information to relate the variables, you can just substitute and get rid of it, right? If they don't just come right out and tell you, then you have to actually do a little thinking.
Can we just plug in?
That's a very good question. Can you just plug in 10? I have that relates to now like 5 different questions I'm going to ask you, all right? Okay. Question number 1. When I'm talking about dV dt equals 10 here, am I talking about the volume of the tank or the volume of the water in the tank?
Volume of water.
Volume of the
The water. Because is the tank's volume changing?
No.
No, right? The water in the tank is changing at a rate of 10 cubic feet per minute, right? Okay, so this rate of change is the rate of change of the volume of the water. This height, are we talking about the height of the tank or the height of the water? Height of the water. Now the water, because it's water, is still cone-shaped, right? Does that make sense? Okay, so it's still a cone, but this 10 by 12 dimension, is this 10 by 12, are those dimensions for the water or the tank itself?
The tank.
Those are for the tank, right? So, can I plug in, and then here's my next question, is this 10 a radius or a diameter? It's a diameter, right? So the actual radius of the tank would be 5. Now, if I were to plug in a 5, first of all it would be wrong because is this formula going to be for the tank or the water in the tank? Water in the tank. So if I were to plug in a 5 for the radius, it would be the radius of the tank, not the water. And then the other problem, of course, is, say I did know the radius of the water. Is it a constant? No, it's changing. If the radius of the water, as the water fills the tank, that radius is not staying constant. It's not like it's forming a straight up tube in the tank, right? It's conforming to the sides of the tank. So the radius changes as the water increases, so you may not plug a number in here because the radius is not constant. So we've got to figure out another way. See how much, look, that one little question led to so much discussion. So we have to figure out another way to approach this. Alright, so this takes a little geometry. And remember, I'm going to tell you, this is the hardest problem we're going to do today, okay? So it takes a little geometry. I'm going to call this dimension r, because that's the radius of the water, right?
Right.
Okay. I'm going to extend this line up to the top of the tank. Now, this line, the top of the tank and the top of the water, those lines are parallel. So you could think of this line as 2 parallel lines cut by a transversal, right?
True that.
Okay? Now, because of that, these are corresponding angles, right?
Yeah, right.
Okay? Now, if we think of this as a great big triangle and this is a little triangle, this angle right here, of course, is congruent to itself. They share the angle. So we have 2 triangles with 2 congruent angles. What can you tell me about those 2 triangles?
They have the same ratios like lines.
You are absolutely right, because those triangles are, no, similar. They're similar, right? By the angle-angle similarity postulate, right?
Yay!
Yeah. Okay, so when we have 2 similar triangles, Mustafa, you were absolutely right though. What do we know about similar triangles?
They have the same like ratios.
The side ratios are they're all proportional, right? Okay, so we can write a proportion for our radius and our height of this triangle compared to the radius and height of the big triangle. Whenever you need to write a proportion, put the letter you want to get rid of on top. So we want to get rid of the r, so we're going to write r, I'm going to do it down here, r over h equals, so the radius to the height of the little triangle equals what to what?
5 to 12.
5 to 12.
And then h is 8, right? No.
Is h constant?
Alright, you know, I just don't want to talk to you anymore.
Guys, don't plug in numbers. Please avoid the urge to plug in those numbers until after you've taken the derivative. Alright, so r is 5/12 h. So what we're going to do now is we're going to replace the r in our volume function with 5/12 h. Okay? Please do not differentiate this, because this, of course, would require what rules? Chain rule and product rule, right? It'd be kind of a, you could do it, it's just it'd be a little messy. It's much easier to simplify first. So if we simplify this first, so we get 25 over 144, and then h squared times h gives us an h cubed. This I can differentiate, right? This is all just one big ugly coefficient, right? All these numbers. Okay. So here's what I have now. Moving over, my dv dt equals 1/3 pi times 25 over 144 times, we need the derivative of h cubed.
Bring down 3.
So 3
times 25.
3h squared dh dt. Okay, it's a lovely derivative, and now we could just plug in our numbers. So dv dt is 10. Can I cancel the 1/3 and the 3? You guys okay with that?
Yeah.
Okay, equals pi times 25 over 144 times, what's h?
8.
8! See, now you can plug in 8 squared dh dt. So dh dt, let's figure out what's going to go on the top and what's going to go on the bottom. So I'm getting all this stuff over here. So I have a 10 on top. Where's the pi going to go?
Bottom.
Bottom. Where's the 25 going to go?
Bottom.
Bottom. Where's the 144 going to go? Top. Where's the 8 squared going to go? Bottom.
These price laughs at like an 8.
What are my units?
Feet. Now should be
Feet per minute.
cubed per minute.
Feet per minute.
Feet per minute.
Is it feet or feet cubed?
Feet.
Or feet squared?
It's right there.
No, I see right there.
Remember, this is the units of height over the units of time. Height is measured in feet, time is measured in minutes, feet per minute. Alright? So tonight, in one of your homework problems, that is like almost this one, it might even be number for number the same. In one of your homework problems, you will have this exact same problem. If you're not given the relations straight up, look for similar triangles. Alright? Okay, one more problem to do. And then if there's time, which there won't be, if there's time, I have another problem to do, but I have several things to talk to you about with this problem. Okay, so let me just make sure I'm getting the whole thing
Alright, so you
in.
see 10 equals
I
and
back
all
up
that.
a little.
Just imagine all that in parentheses, and then DHT multiplying all that, and then shoot that, and then.
Okay.
She's done.
Okay, so,
She didn't move the DHT, she moved everything but the DHT.
right, I kept the DHT.
Oh, I see. Never mind.
It's like
All right.
she's Harold Houdini.
A spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Find the rate of change of the surface area when the surface area is 64 pi. Now, there are, I don't know if I've mentioned this to you guys yet or not, but there's multiple ways to solve related rates problems. I do them a certain way, and I've been taught different ways. When I was in college, I had to do them a different way. Mr. Jones does them a different way. This problem is actually easier to do using the method that Mr. Jones likes to use. The others are really potato. But this one actually is easier using his method. I'm going to show you my method first, And then if there's time left, I'll show you his. If there's not, I'll show it to you tomorrow. Okay? And then you can decide. Some people, once you learn one method, you don't want to have to sit there and juggle between two. So you might want to just stick with it. But just know there's always another way. Right? Okay. So here's what we have. Spherical balloon is being inflated at a rate of 10 cubic centimeters per second. What does that represent? dV dt.
I know. Honestly, tough words.
Okay, so dV dt is 10. Find the rate of change of the surface area. So what are we looking for? Yeah, I'm going to call it ds dt so we don't confuse with just area. I have a whole story about that. When the surface area is 64 pi. So we're looking for ds dt. So what would be a decent equation to use for this? Surface area of a sphere, right?
Which is like 4/3 something. Right?
Close. 4 pi r squared.
See how this goes.
Yep. We want ds dt. Do we know or want dr dt? We don't know it and we don't want to know it, right? So r needs to go. We're given dv dt. How could we use dv dt? We can't substitute r for dv dt. So maybe we should write the volume equation too?
Yeah.
Just for the heck of it? Hey, volume, that's your 4/3 pi r cubed, right? Now you could technically solve this for r. R would be the cube root of 3v over 4 pi, and then plug that in there and square it, and then do the derivative, but it would not be pretty, right? You could do it. An easier way is to actually go ahead and take the derivative of the volume. And what we're going to do is we're going to solve for dr dt, and we'll use that for our dr dt in this problem. Okay, so it's like kind of like a little double substitution kind of thing. So here we go. dv dt is 10. 4 pi r squared, I can trick you and say this is actually just 64 pi, because what is 4 pi r squared?
Oh, the surface area.
It's the surface area, so you can just replace it with a 64 pi. But if you wouldn't recognize that and you want to solve for r and do the whole thing, that's totally fine, right? You'll get the same answer. So anyway, 64. I think we're going to have to solve for r in a minute anyway. 64 pi dr dt. So dr dt equals 10 over 64 pi. Now I go back to my surface area equation. Walk me through the derivative of surface area.
ds dt.
ds dt equals 8 pi r. Don't forget the dr dt, really important. Guys, every time you differentiate, you're going to be putting one of those d something dt's, right?
Right.
Okay, don't forget those. All right, ds dt is what we want, so we need 8 pi, we got to find the radius, but dr dt, hey, we know it, it's 10 over 64 pi. Now, how do I find the radius? Well, I was told the surface area is 64 pi, so I know 4 pi r squared is 64 pi. Kill the pi's, kill the 4's, and your radius is 4. If you clean it up, so 32 over 64, so that becomes a 2, kill, 5, pi's cancel. This whole thing just equals 5. What would the units be?
So ds dt is 5.
What are the units?
Centimeters per second.
Centimeters per second?
Square.
Centimeters what? Why is it centimeters squared? Because it's surface area, which is measured in centimeters squared, right? Centimeters squared per second. All right. Now, tonight's homework is how many problems?
8.
6.
6.
You are not allowed to skip any of them. I want to see at least a setup, what you're given, what you're trying to find, and your best attempt at an equation that relates to variables. For at least anything that are similar to the examples we did here, you have to do it all the way through, right? If you are a junior, please don't